Good morning, everyone. My name is Venkat Guruswamy, and on behalf of the Simons Institute, it's my great pleasure to invite you all to the Quantum Industry Day. A few words about the Simons Institute. We opened doors in 2013, thanks to a very generous grant from the Simons Foundation in 2012, which still continues to support us. And the Simons Institute is the world's leading venue for collaborative research in theoretical computer science and related fields, including obviously quantum computation. And by any measure, the Institute has had a tremendous record. In particular, just one measure, it's brought over 4,000 long-term visitors in the in the 12 years it has been operating. Its main mode is to convene thematic semester programs on topic of great current interest and promise, but realizing that there are certain topics which are just really exciting across the board, and we also started activities which are longer term, and that led to the Quantum Pod, which is really a period of sustained activity at the Institute through visitors, workshops, postdocs, and thematic semester programs on a periodic basis related to quantum computing. And so I said something about quantum. We are in the Quantum Industry Day, so I want to talk a little bit about the industry as well. Now, if you think about computer science, it is such a high-impact field precisely because of the amazing industry we have, which can really literally transform our world in a matter of few years, and a lot of it happening right here in the Bay Area. So industrial connections are really important to us so that what our work is relevant and really can have the impact it can. And quantum is really a poster child for that, because it's really one of those areas where the synergy between theory and practice is important. A lot of the most high-impact work is really based on co-design, taking lots of factors into consideration. So really hope the connections with industry will really have even more impact than the theory research. And so just as an example of that, we have a really exciting day of talks today. I had to take some meetings today, so I was looking for some gaps where I could squeeze something in, but no, nothing. Every talk looks amazing. So I'm really looking forward to it. And with that, I'll let Umesh Vazirani, our Quantum Pod Director, to introduce the scientific program.
Thanks, Venkat. As Venkat said, the Simons Institute is really a mecca for theoretical computer science and for interdisciplinary research. So I'm really happy to welcome you to our fourth annual Quantum Industry Day. Well, this year is quite special, coming on the heels of the Nobel Prize in physics, in quantum computing, and for work done here at Berkeley. So it's a real honor to have John Martinez back there joining us. And I hope, John, you'll take a few minutes to reminisce during your talk about I hope you'll take a few minutes to reminisce about the work in your talk. Okay. Yeah. Okay. Yes. Great. Good. Okay. Excellent. Looking forward to that. Okay. So in quantum computing, we have come a long way. But it's a great endeavor. But there's a really long way to go yet in the to get to where we want. And so that leaves a lot of room for cooperation, given that the horizons are so far away, and especially I think cooperation, between academia and industry. So many of us have a good dialogue with industry, but during this industry day, it would be good to explore whether we can make some of these interactions much more robust. So, okay, so how could we do that? Venkat talked about a few things. Let me just say one thing that came to my mind. The Simons Institute's DNA makes it a perfect catalyst, for bringing groups together and for supercharging research. And so, the question that occurred to me is whether we can explore ways to make this happen also between, bringing industry and academia together. For example, we run these summer clusters in quantum computing, and perhaps we can dedicate one of these to actually bringing industry and academia together in this supercharged way. So perhaps we can explore this, during the breaks and afterwards. I look forward to conversations with you on this. Okay, so with all this, let me introduce our first speaker. It's a real pleasure to have Craig Gidney here from Google. Craig is actually an industry unto himself in terms of doing this remarkable, ways of doing resource allocation in quantum algorithms and figuring out ways of speeding up algorithms, in ways that we wouldn't have thought possible. So Craig, really looking forward to you talk. Sure.
Do I have the mic yet? All right. So let me reset my timer. All right, hello everyone. My name is Craig, and I'm going to be talking about optimizing costs by basically paying attention to implementation details, which is probably appropriate for an industry day. Because everyone loves a good, abstract optimization problem, something elegant and simple that ignores the details that don't matter. But it's important to notice when optimizing those abstractions starts to differ from optimizing the reality. Some context for this talk is that one of the things I do is make sure cryptographers are better informed about the cost of quantum attacks. So for example, over the past decade, the expected cost of factoring has dropped by 3 orders of magnitude. And it would be disastrous if people trying to prepare for this thought it was 1,000 times more expensive than it actually is. Their timetables would be way off. That's why I do it. Anyways, I think one of the things that make these papers interesting is that they try to give physical qubit estimates instead of logical qubit estimates. And doing that well requires going beyond just the abstract logical circuit. Now, concretely, this talk is going to be about optimizing adders. I'm going to talk about classical adders and quantum adders and how we've improved them. But the adders are really just a specific example of this general pattern of the details mattering. So let's start by just looking at classical adders for some context. If you've ever taken a computer architecture course, you've seen diagrams like these. These are logic circuits for doing addition. On the left is a full adder, which ironically isn't an entire adder. It's just one step of a ripple carry adder. If you make a chain of these full adders, then you get an entire adder, a ripple carry adder. Here's a physical example of a ripple carry adder built out of dominoes. It takes a long time to set up this adder, and you only get to use it once, but it's fun watching it run. If you want to see that, you can watch the linked YouTube video. It includes an instance of what I'll call a domino crosstalk error. Here's another physical example of a ripple carry adder, also from a YouTube video. This one's made out of water and siphons and other trickery. And here's yet another one. This one is built out of redstone components in the game Minecraft. And here's even another one. This time it's in Conway's Game of Life. So these 4 examples are all the same circuit. They're all ripple carry adders. But I hope it's really obvious that in each of these contexts, the optimization problem of making the adder smaller has a very different character. If you try to build the Minecraft adder as if it were a domino adder, that won't go well. For example, the Minecraft adder is 3-dimensional, whereas the others are mostly 2-dimensional, and this hugely affects wiring. Another detail is some of these are one-time use, so the setup costs are a major concern. The water computer isn't even clocked, it just kind of eventually gets to the answer. So there's lots of crucial differences here. Here's one last example of a classical adder that's maybe a bit more obscure than the Minecraft one, but this is a magnified image of the adder from the Intel 8008 processor from the 1970s. Surprisingly, for an 8-bit processor, this isn't a ripple carry adder. It's actually a carry look-ahead adder, which is lower depth. But mainly, I want you to notice that there are clearly details here beyond what's in the logic circuit. There are geometric constraints and electrical constraints and manufacturing constraints, and if you try to ignore that stuff, you won't be able to understand why this thing is the way it is or how to make it better. Okay, so that was classical adders. Let's talk about the same thing, but quantum. And basically, a quantum adder is just a classical adder, but built with reversible gates instead of irreversible gates. That's not universally true. There are very interesting adders, like the Draper phase adder, that aren't built from reversible classical gates. But From a fault tolerance perspective, those tend to be quite expensive, so I won't be talking about them. On this slide, I'm showing the Kikaro adder, which uses 2 times n Toffelees to add 2 n-qubit numbers, and it only requires 1 qubit of workspace. It's a nice adder. Here's another quantum ripple carry adder, which is actually from my first published paper. It uses ancilla qubits to save half of the Toffelees versus the Kikaro adder. So this is an example of a trade-off that you can see in the abstract circuit model. The trade-off being, do you want to pay more qubits or do you want to pay more Toffelees? Although, as you'll see later in the talk, this apparent space trade-off may be a bit misleading. So we need to physically implement these adders. And I happen to work on a superconducting qubit team, which is going to hugely color the talk, where currently our plan is to do the surface code with planar connectivity. And to understand the cost of planar surface code computations, we draw diagrams like this one. We call these defect diagrams, and essentially they're just showing locations and times of changes to the background pattern of surface code. And because surface code computations are topological in nature, operations correspond to certain shapes or linkages in these diagrams, which makes them very nice if you understand them. Unfortunately, I don't have time to explain the notation beyond that. Just be aware that this circuit diagram in the top right has to be translated into this type of thing before we can execute it. So importantly, if the circuit diagram and the defect diagram disagree on what's expensive, the defect diagram wins. Anyways, this figure is from a 2018 paper. And at that point, we were still imagining using braiding to implement surface code operations. Also, at least in this particular paper, we were using a very simple strategy for correcting the teleportations that we use to do the T-gates. So here we're doing a teleported T-gate, then waiting for the decoder to determine whether a correction is needed, then maybe doing the correction, which takes quite a lot of time because we don't have transversal gates, and then that process repeats. So that's what this diagram is showing. Now here's a figure from a year later. By this point, we decided to switch from braiding to lattice surgery, which you can actually tell visually by the fact that the defect diagram in the bottom left has 2 colored pipes meeting at junctions rather than single colored pipes braiding around each other. In addition to that change, we'd also come up with a different strategy for doing the corrections. Basically, instead of attaching the correction to the target qubit, you can attach it to the magic state that you're teleporting through. And this is hugely beneficial because the target qubit is going to be in the middle of this whirlwind of activity. It's in the middle of the computation, and it can be hard to reach. Attaching to the magic state is much easier because it can be done far away from the whirlwind. Furthermore, you can arrange things so that the correction is performed not by including a slow S gate or not, but rather by switching between measuring in the X basis or the Z basis. Both of those operations are transversal, even under planar connectivity. And so the correction can now be very fast. And basically, when you do things this way, your logical clock speed, at least in the case of superconducting qubits, would be determined by your decoder's latency, as opposed to much by the physical part. Once you have this idea of attaching the corrections to the magic state, you can just grind through the details of doing this for all the corrections created when teleporting a CCZ gate, which is the terrifying diagram shown here. And of course, you can also do this for a T-gate, which Daniel Litinski got to before we did, actually, in his nice Game of Surface Codes paper. Now, that circuit diagram from the last slide is very cumbersome. Personally, I strongly prefer drawing these things using the ZX calculus. In circuit diagrams, this auto state transformation is kind of very unusual. It's inconvenient to write down. Whereas in ZX graphs, it's sort of very natural. And this is a bit of a tangent, but it really reminds me of how people used to do algebra in full English prose rather than with symbolic manipulations we do today. You know, problems get a lot easier when you have the right language. And I think, at least for this autocorrection concept and many others, ZX graphs are just a way better language than circuit diagrams. And I realize this is really ironic in a talk about details because ZX is more abstract than circuit diagrams. But it turns out the extra freedom from the abstraction actually often allows you to represent the details correctly. Yeah, one of the most common recommendations I make to people in quantum computing is that they should learn the ZX calculus. Like, seriously, you won't regret it. In my eyes, nothing in fault tolerance makes sense except in the light of ZX. Anyways, now that the Clifford correction can be put somewhere else, the design problem for making an operation like an adder in lattice surgery gets a lot simpler. There's a Toffoli gate inside of it, but that can be fueled by an auto CCZ state, and the corrections are somewhere else, so we don't have to worry about those. So we need ports to attach the state to the block, but otherwise we can just convert the circuit into a ZX graph, convert the ZX graph into lattice surgery, and then put a nice shiny blue box around it so it looks clean. A particularly cool thing about the corrections being elsewhere is that these blue boxes no longer need to occur one after the other. They can be spread over space instead of being spread over time. And this allows you to do more work in parallel. There are still time dependencies between the corrections. So if we do too much parallel additioning, we'll create correction waste faster than the decoder can resolve it. But this is hugely freeing compared to inline corrections to be able to not really care about time for at least this part of the setup. Here's a more integrated layout of the adder. As mentioned, the blue boxes are each a step of the ripple carry addition. You can see, if you look closely, that each blue box has red lines leading to one of the big red boxes. Those big red boxes are the factories making the CCZ states. Also attached to the red lines are these pink boxes. That's where the corrections are being done. The pink boxes are turning the CCZ states into auto states. And if you look really closely, you'll notice there's actually 2 pink boxes per red box, not 1. And that's because these pink boxes leave behind these qubits that have to be measured in the X or Z basis to do the correction, but it might not be known right away what to do. And when you're doing a lot of adding, you may have to put another layer of this stuff above it, or in the future. And if you put the pink box in the same spot, it might hit itself. So there's just 2 locations that you can switch between, is what the diagram's trying to show. So I've very roughly described now an execution strategy for adders, or just really any computation, of attaching corrections to the magic states and doing what we call reaction-limited computation. There are other execution strategies. For example, in his Game of Surface Codes paper, Daniel Litinski explains what's called deferred Clifford computation. I'm not going to explain this. He does a really good job explaining it in his paper, and it's a very elegant system, so people love to use it. It's also kind of really inefficient because it causes every operation to touch every qubit. Actually, Weber et al. Did an estimate where they found that this deferred Clifford-style computation was orders of magnitude less efficient for the same algorithm. And in 2022, Litinski put out another paper describing another execution strategy he called active volume. That one's also much more efficient. It actually kind of annoys me when people use the deferred Clifford compilation for estimates because it's really not optimized for that, especially if magic states get cheaper, which is kind of an important detail because magic states got cheaper. So here are defect diagrams showing, so everything I've been talking about until now was like 2019 timeline. So here are defect diagrams showing T-state preparations, one from 2018 and one from 2024. Both easily achieve error rates well under 1 in 10 million, and in fact, much better. But the 2024 construction is between 10 and 100 times smaller in expectation. In the context of our adder, the magic states getting smaller is kind of annoying. Those big red boxes from a few slides ago contained within them many of these T factories that are now disappearing. They're just gone. Also, we did get better at layout and found more compact ways to lay out the factory. So, end of the day, back in 2018, the size of these blue adders basically did not matter. You can see there's a lot of unused area on the right around the blue box because the spacing is really being set by the factories. And those red blocks are just now much thinner, like 3 patches wide instead of 12 patches wide, making them narrower than even one of the blue blocks. So we have a problem. To fully benefit from these smaller factories, we need smaller adders. I won't bore you with the rather large variety of things I tried that didn't work to make the adders smaller. I'm just going to tell you the thing that did work. I would consider it a bit counterintuitive because it starts from this identity for addition that uses way more operators than the usual ripple carry adder. But if you look at this expression with lattice surgery eyes, what you see is not 9 values being combined, but rather 3 parities being combined. Parities are pretty cheap to access in lattice surgeries, which is why you'd even consider this. Anyways, if you write down a ZX graph implementing this identity, you get this thing at the bottom. The 3 parity operators are the 3 columns. And the AND gate is being achieved by attaching an auto state to the top. Something I never noticed when I was making adder circuits, but I noticed right away once I had this graph, is that for every qubit, the input and the output of that qubit are connected by a path that only passes through nodes of one color. This is interesting because in the ZX calculus, monocolor connected components are basically just like one big node. And because of that, it was sort of obvious that I could grab the output edge, drag it over to the input edge, and have the input and output meet at a blue node before they entered the diagram. So essentially, instead of passing qubits through, you could have the qubit sit in place and split off what we call a z-copy or a z-split, and merge that into the operation. And this is really nice because it cuts the number of ports in play in half. There's just going to be less routing cost. And that then enables a bunch of other optimizations. So for example, this adder block involves the previous index and the next index for the bits. And you can arrange things so that the previous index ports are on the left and the next index ports are on the right. And that enables you to tile this thing very naturally by attaching it to itself left to right. And you can still get the input qubits in from the front. And then the magic can come from the back. And this ends up being nearly 4 times more compact than the 2019 adder block that I showed earlier. Here's that more directly shown. And just to kind of really harp on this point, none of this is really visible from the logic circuit diagram. These are both ripple carry blocks. They kind of come from the same circuit, you could argue. They have different layouts. They have different calling conventions. They have different sizes. But none of that is really visible from the circuit. Here's a mock-up of a more worked out example of what this adder block looks like in context. There's 2 things I want to point out here. First, green and blue tinted pipes are related to the Clifford corrections, and they are really standing out now as a dominant cost. We should probably try to improve that. Second, there's this hallway down the middle. I'll actually try to point this out if I can get the mouse over here. This hallway here. That's being used to get the inputs to the adder block, and then it's also being used to send the output back, and then the output's actually being dropped in the hallway. So as the adder runs, it's filling in the hallway. If you remember earlier, I said the space overhead of my adder versus the Kakaro adder was potentially misleading. This ability to drop things in the hallway is what I was referring to. So the Kakaro adder would also need these hallways to be present because it still has to get the inputs to the addition area. So it also has the hallways. It's just not also using them as storage. So essentially, this trick of dropping stuff in the hallway is removing the space trade-off. This is another example of something that would be kind of completely invisible to you if you're looking at the logical circuit. And in fact, in this context, I would argue that oversight would cause you to pick the wrong adder. I should mention, I've been saying you can't see these in the logical circuit. You can obviously translate this back into the logical circuit. Somehow, everything is possible to express in quantum circuits. It's not impossible. It's just kind of slow to do, and it comes out looking very unusual. It's not typically how people write these things down, and frankly, these circuits are pretty tedious to manipulate. As a side note, there's some other optimizations that I didn't discuss related to balancing the number of corrections during the forward and reverse pass. But anyways, when I designed this lattice surgery adder, I did attempt to translate it back into a circuit, which is shown here. Again, it looks sort of horrifying. It's very large, very complicated. But this allows us to do a comparison. So here's the adder block from 2017, from my 2017 paper, versus the one from 2025. The 2017 one uses fewer gates, fewer ancilla qubits, and that is completely misleading to say because it's the more expensive one. The reason the numbers are misleading here is that the 2 circuits are different levels of distance from implementation. So all of the apparent extra cost in the 2025 circuit is also present in the 2017 circuit. I'm just not writing it down. It also needs magic states. It also needs Clifford corrections. It also needs access hallways. Don't let the notation fool you. One last thing I want to mention about the adders is actually kind of a dumb mistake that I made. We were hosting a student researcher, Christopher Kang, and he was looking over these diagrams, and he pointed out to me that thing I mentioned earlier about not running into yourself in the future, I completely did here. If the corrections have to stick around for a while and you tile this on top of itself, it hits itself. So I'll have to fix that. I'm not too worried about that. One of the reasons I'm not worried is in the paper this is from, I am aware that I often make little flubs like this, and I left myself slack space. You can see the slack space here on the right, and also slack time to absorb anything like this. These kinds of things are why I prefer to have everything checked by computer if possible. And in fact, many parts of the adders that I've shown here are checked by computer. But that can be very slow to set up compared to just drawing things in a 3D modeling program. And sometimes I'm lazy and things like this happen. Anyways, what can we take away from all of this? I hope I've convinced you that circuit optimization extends well beyond reducing gate count or gate depth in the abstract circuit model. And it's not like the improvements I was describing were negligible. The adder block got 4 times smaller. the deferred Clifford compilation was hundreds of times slower. I guess I'll note, this is particularly dangerous when you optimize to the wrong thing, because when you really start optimizing hard, when you squeeze hard, you tend to sacrifice the thing that actually mattered. Because when you really start to squeeze, you make all the trade-offs in the world just to make the number you're trying to go up, go up. So I think it's really important to understand the actual problem, which in practice tends to translate into just being aware of how the things you're writing down get implemented, knowing the level below you. And I'm basically going to end the talk by giving a bunch of examples of really important implementation details that QEC theorists like me love to ignore. First, we have leakage. So in a typical quantum error correction paper, including most of mine, you'll see diagrams like the one on the left. What we actually run on hardware is more like the one on the right. You'll notice, for example, it doesn't just have one reset, it resets twice. And between the two resets, it's doing this weird operation, which isn't a stabilizer operation. It's designed to pull leakage out of the data qubit into the measure qubit so it can get reset. So we pay substantial cost to do this. These operations are not free. And most papers just are completely ignorant of this cost, and so it's impossible for them to improve on it or to shape it or anything like that. Another one is cosmic rays, or more generally, high energy events. So on the Google team, when we push rep codes out to big distances, we see noise floors. And when we put in mitigations for high energy events, those noise floors go down, as you can see in this diagram from the paper where we showed we could go below the surface codes threshold. Ideally, you could completely mitigate this in hardware. This is already good enough that you could maybe just ignore it and hope that you don't get hit. But it's conceivable you might have to fix it in software with error correction. And if so, that has major implications on how you compile things. Because basically, you always need to be ready to take a hit. And that causes you to have to be cautious in how you do the layout. You always need to have an escape route, essentially. Another detail is connectivity. So for years, for decades even, people thought you needed 4 neighbor connectivity to run the surface code well. Then we found out that's just wrong. You can do it with 3 neighbor connectivity. This is potentially very enabling for hardware because it reduces the amount of stuff on the chip. It reduces the number of wires. It reduces constraints within calibration. This could be very useful. Although I will note it somewhat conflicts with this next one, which is dropout. So when you manufacture your qubits, what you make can just be broken. If your error correcting code can't handle qubit dropout elegantly, you are sort of essentially demanding that your fabrication team achieve 100% yield. And for a small system, you can get lucky on that. You can just keep rolling the dice until you get a chip where everything yielded. But for a big system, that basically becomes impossible unless you're perfect. And classical fabrication is sort of amazing, the yields that they achieve. So that's not inconceivable that you could get away with this, but it's nice if you can take it. And actually, I think this is a detail that a lot of the fancier codes that people are imagining I worry about may cause a lot of problems, is they may not handle dropout well. I also had one more example. Actually, it was my favorite one, but I was told I probably shouldn't mention it. So as my final act, I am going to leave you in suspense. And thank you for listening.
Time for a few questions.
So, Craig, I want to thank you for the whole field. You keep coming up with these really amazing ideas that improve the way the qubits work and the way the algorithms work. And I know you didn't come from the standard physics background. And I was wondering, could you share, how is it that you keep on coming up with these great ideas? And maybe it's because you have a different background. I don't know.
I also don't know. Like the muse strikes. I would say one of the things that I notice myself doing that is less common is I write tools to simulate the systems and make it easy to manipulate the systems and then use those tools. And this is a way of building intuition because it can take a long time to work out the consequence of something with pen and paper, but the computer can do it billions of times faster. And there is user experience research that shows if you can get basically the time between when the computer is told to do something and when it shows you the answer, below 100 milliseconds or 10 milliseconds, then it just sort of feels like a thing that you're manipulating instead of asking questions and getting answers. And I think this is very conducive to building intuition.
But I would say this is standard, when you do classical computer algorithm development, you build simulators all the time. So it's kind of like using the best practices of computer science to kind of figure out how things work in this way. Is that a way to think about it?
I think of it as I trained as a software engineer, and I think of it as applying that to the field and benefiting enormously from it. As a concrete example, I have a paper on doing Y-basis initialization in the Surface code, and it's a somewhat complicated circuit, and I couldn't get it right until I was forced to write a tool to edit it visually, which is called Crumble and is on the internet. And sometimes I spot people around the office using it.
Okay, thank you.
For the dropout, can you model it as erasures, or is it something different?
Dropout is sort of like a highly time-correlated erasure. It's an erasure that keeps happening constantly. So at least for a superconducting qubit, this is it literally does not function. In some way, you send signals to it and it does nothing. If it's really bad, it might actually take out the neighbors around it. In a different context, like in neutral atoms, this doesn't really translate because they would just substitute in another atom or something.
Thank you for the talk. So I think the error correction architecture hasn't been established yet. So in a sense, you might use different code or something. So do you think your architecture can be transferable to different code architecture? Or which part can be transferable? Which part should be changed? Yeah.
So I'd say a major constraint on superconducting qubits is the planarity constraint. Although IBM is trying to change that, and maybe they'll succeed. So for transferring to other codes, one of the first things I would look at is if I have to embed this onto a plane, what does that do to me? So that makes, for example, the color code a very interesting candidate, the honeycomb code a very interesting candidate. But I'm just trying to think of an example that wouldn't work at all. Some highly non-local code with just random connections would not work very well for superconducting qubits. We pick our codes based on our constraints.
Great. Thanks a lot, Craig.
Sure.
Great.